Today we want to discuss about quantum mechanics and the discovery of, or the beginning, I should say, of the journey of how to describe atoms using quantum mechanics. Okay, so uh, the idea of atom is very, very old. It comes to us from the Greeks. I think it was Democritus who proposed the idea of atoms, but it was only in the 20th century that the idea of atom was firmly established. Okay, so I think in 19th century, even in 19th century, rightly so, a lot of physicists were skeptical because they couldn't accept something that they couldn't see with their own eyes. And of course, atoms are so small that we can't see them with our own eyes because our eyes cannot register the wavelength of light that is needed to see atoms, right? Because atoms are very small. So the frequency of light has to be very, very high for the wavelengths to be very small. Yeah, because you cannot actually see something with a wavelength of light smaller than an object, right? So for example, if you have a human being and you have, say, I don't know, a plane, like a fighter jet, with a radar, you won't be able to see a human being. So this is basically a radar wave because the size of a human being is smaller than the wavelength of the radar waves, right? Whereas the plane, its size is around the same. It's bigger or around the same wavelength as the radar wavelength. So similarly, if you want to see atoms, you have to use very, very small wavelength and high frequency light. And that's not something that basically we can see with our eyes. So the other thing was that, as I mentioned last time, is that one of the contributing factors, so Ludwig Boltzmann was a big proponent of the atom. His ideas of statistical mechanics, and he has done some amazing work in both equilibrium and non-equilibrium statistical mechanics. Just one second. So yeah, Ludwig Boltzmann had done a lot of work both in equilibrium and non-equilibrium statistical mechanics. The fundamental equation for non-equilibrium statistical mechanics is known as the Boltzmann equation, and it's an equation that is extremely useful in, say, cosmology. So he had built his ideas around the idea that he had basically bet on the atom, if you like. So people say that he also suffered from depression. People say that the fact that atoms were not widely accepted as Boltzmann would like to have, wanted it to be, contributed to him taking his own life. Okay, so, but the interesting and the tragedy is that the clincher that established atom happened before Boltzmann had taken his life. He just wasn't aware of that paper. And that paper was by a young Albert Einstein in 1905. It was one of his famous 5 papers that he produced in his miracle year. 1905 is called his miracle year. And what Einstein showed was that he explained, Einstein in 1905 explained Brownian motion in terms of atoms and molecules, okay? So wherever you have atoms, you have molecules. They come hand in hand, these two ideas. So what is the idea of, what is Brownian motion? So Brownian motion is named after an English priest. I think his name was Robert Brown, if I'm not mistaken. And what he noticed was that if you try to suspend very small, but still visible using a microscope, particles of, say, pollen, or in water or other liquids. So suppose this is a pollen. I'm exaggerating. Usually you can only see that with a microscope, but it's still visible. Then for heavier particle, say suppose for heavier particle, if you drop them in water, they will fall in water more or less in a straight way. But the pollen particles, Brown observed, was that although in general they have a drift downward, they exhibit random motion. And this, like in modern StatMech language, this Brownian motion is called a random walk. So, and the random walks are very, very useful, and they're an active field of research because they have applications in many fields, including even like protein folding and things like that. So anyway, what Brown noticed this, and therefore it was called Brownian motion. So then what Einstein said that, well, if the liquid in which these particles were suspended consists of, say, atoms, then you can get a consistent picture of what's happening. So suppose that this is the pollen. So this is magnifying it. And then there are, atoms hitting it from all sides. So if the atom is small, but relative to the size of the pollen, they have some significant size, right? So the pollen or the particle is light, and because of their smallness, there is a net significant force on them in some random direction to cause a change of momentum in that direction, okay? So why does that not happen to you and me? Why aren't we always, swayed by the random motion of air around us? Why do we not go left or right, or when we're in, say, still water? Can someone answer me?
We're too huge.
We're too big. Even if there is a tiny, net force on us due to the water, it's it's not enough to create enough of a momentum change in us. So this is a very beautiful and elegant explanation. And what Einstein showed that this motion can actually be used, can be measured on average to predict the value of this number. And the value of Avogadro's number come out to be roughly the correct value. And what Einstein further showed was that if in the limit where the Avogadro's number go to infinity, so that is the limit in which the atoms become so small that it becomes a continuum, the random motion disappears, okay? So in that limit, the Brownian motion disappears. Okay, so this was an important paper, a milestone in establishing the atomic theory of matter, okay?